So we've hit on the ideas of matrix addition, and with a little tweak we can say matrix subtraction, but it's not really subtraction, it's still addition, and that was using multiplication by a scalar number, a fixed constant number. We talked about matrix multiplication, and so there needs to be at least something to at least kind of dance around division. So remember that the idea with division with regular numbers is something that we could talk about as division. For instance, I can take a number and divide it by 2. Or I can take a number and changing from division into multiplication, I could say, instead of dividing by 2, I can multiply by 1/2. So there's this kind of reciprocal idea that I can use. Instead of dividing, I can multiply by a reciprocal. We're going to use that manner of thinking to address more with matrices. Since we don't have a way of doing division with matrices that would be in any way something simple, because as we've already seen, multiplication, well, it can get involved enough as it is. Trying to then handle division would probably only complicate things further. Is there still something that we can come up with that would use the multiplication by a reciprocal kind of idea? So is there a way, if we start out with matrix A, is there a way of finding just the right matrix that if we do multiplication out front and multiplication out back, everything will work out the same? Specifically, we'll get a square matrix. That's the identity matrix. So just the ones along the diagonal, zeros below it, zeros above it. If we can find just that right kind of matrix, we're going to call it not a reciprocal, but we're going to call it the inverse matrix. If we can find just that right matrix, then what we've got is something that will in fact work with that idea of division without it being division. It's, again, this reciprocal kind of idea, but we're not calling it a reciprocal, we're calling it an inverse matrix. So still using some terms that kind of catch those ideas. Now we've got a few different ways that we can go about this, and of course I'm sure the one that you're most interested in is going to be the calculator one, which is the last one I'll talk about. But if what we're looking at here is we want to figure out a matrix that is going to work, and so what we'll do is we'll come up with a generic set of matrix elements. X, Y, if we need more, X, Y, Z, W, or A, B, C, D. We'll come up with a generic matrix, and we'll do the multiplication and get a system. Hardly seems to be helping things, does it? We go from wanting to use matrices to solve systems to now having systems help us try to figure out other matrices. It seems a little circular and kind of more work than we might like. But this is legal. So, as a for instance here, if we have, and to try to keep it mellow, we go with a 2 by 2 matrix. That means that what inverse we're looking for is also 2 by 2, which has 4 entries. So we would be trying to work out a system of equations that's going to end up having 2 of our variables, and then a second system with a separate 2 pair of variables in them, and having to work through all of that to come up with those individual entries, and then checking to make sure that both orders, both orderings of the multiplication, we think that we've got this inverse matrix. So we've got to do A out front times what we think is our inverse matrix. We've got to do our inverse matrix that we think is working out front of our regular original matrix A, we've got to make sure that all that works out. And so overall, I mean, I haven't even written all this stuff in that I would need to check out, but overall, that's a lot of work involved. Ugh. Ugh. So this is really not a preferable sort of idea, but you never know what might be helpful to you as you work through things at any point in the future, so it's worth mentioning. Something that's at least a little bit more in our wheelhouse would be to use row operations. And so here's the sneaky way of doing it. What we'll do is we will take matrix A and we will put it side by side with the identity matrix. Then we'll use our row operations to manipulate the front half of this double-wide matrix so that A turns into the identity matrix. Now what that will actually do for us is that the back half of our double-wide matrix here is going to actually turn into the inverse. So that back half is what we're actually looking for. So again, here is that same set of information with matrix A, getting that same inverse matrix that we got the hard way. But this is a much smoother process to go through. We'll take this matrix, we will work out getting our 1 here in the first entry, a 0 below it, a 1 in the second row in the second column, and a 0 above that. And so through these row operations, which are mentioned here off to the right, the front end of our matrix is the identity, the back end of the matrix is what we want. That should be our inverse, and well, because we already found that at least, we know that that's right, but that would still be something that we would want to double check with that whole thing of take our original matrix times our supposed inverse, take our supposed inverse times our original matrix. We would have to check both directions on that multiplication process to make sure that everything is correctly working out for what we've found. Again, a whole heck of a lot of work, but still something that's doable. So just to nag you with that idea a little bit here, we'll do a larger example together. So first of all, we have our matrix C, and we're going to set that in front of our identity matrix. Since this is a 3 by 3, that means that we've got the 1s along our diagonal, we've got the zeros below it, the zeros above it, and what we're going to worry about is out at the front, we want to transform matrix C into this row echelon appearance. So I want a 1 with zeros below it. Then I want a 1 here in the row 2, column 2. I want zeros above and below it. Then eventually where that 4 is sitting, I would like to get a 1 with zeros above that. Once I accomplish that, the back half of my matrix should be this inverse that I'm looking for. Now in this particular case, at least I already have a 1 in that first row, first column position, and I already have a 0 in the entry immediately below it, so I just need to get another 0 down here in the third row, first column. So we could do a little something like, excuse me, row 1 plus -1 times row 3 to give us a new row 3. So a 1 plus a -1 is 0. A -1 plus a +2 is 1. All right. A 2 plus a -4 is -2. A 1 plus a 0 is a 1. A 0 plus a 0 is a 0, and a 0 plus a negative 1 is a negative 1. The first row and the second row are staying the same, so I'm not changing those at the moment. Well, I actually kind of like the one that's right here, rather than trying to get something even friskier. I could just go ahead and say, let me just get that 1 in the second row. I want to create zeros in the other places, so I'm going to do quite a lot of commentary here in order to come up with the next matrix that I'm looking for that will have a 1 in the second row, second column position. So I'm going to go ahead and put that 1 in there. Basically, the easiest thing for me to do to create that is to, let's say we do these in order, listing from the top. We're going to switch out row 3 and row 2. So that means that row 2 is going to have that 0, 1, negative 2, 1, 0, negative 1. Now, as soon as I do that, though, I'm going to actually start tinkering with that third row, what used to be the second row. So we could actually go ahead and say that we're going to do a let's reference it this way, a negative 2 times that new row 2 plus the new row 3 to give us, just to be cute about it, a newest row 3. So this very temporary row 3 that would have been the 0, 2, 3, 0, 1, 0, we're gonna do negative 2 times this stuff. We're going to add it to that stuff. So again, you'd be a little bit frisky about things if you want. If you want to separate this, you can clearly see that I'm trying to keep this all on one screen. So trying to minimize the amount of work that we have to do to come up with the matrix that we need that has that identity business at the front end and the inverse at the back end. So negative 2 times 1 plus 2 is 0. Negative 2 times negative 2 plus 3 is 7. So 0, 7. Negative 2 plus 0 is negative 2. Negative 2 times 0 plus 1 is 1. Negative 2 times positive, or sorry, negative 2 times negative 1 is negative 2. Positive 2, geez Louise, it's another one of those mornings, huh? Negative 2 times negative 1 is positive 2, plus the 0 would be positive 2. And that's all well and good. But we're going to have to hit up the first row. So we're going to take our new row 2 plus row 1 to give us a new row 1. You see how this is becoming more and more work the more that we have to do, or the more entries that we have. So, all right, Now I'm starting to lean towards using the calculator myself. 1 plus negative, sorry, start at the front. 0 plus 1 gives us the 1 that we still want to have there. The 1 plus the negative 1 gives us a 0. The negative 2 plus the positive 2 gives us a, ooh, sweet, 0. That makes things a little bit nicer. Going back, the 1 plus 1 gives us 2, 0 plus 0 gives us 0, negative 1 plus 0, so that we can finish that row out. So we've got the 2, the 0, and the negative 1 showing up there. Oh, not a big fan, but I've got no other choice really at the moment. I'm going to have to get a 1 there, and the only way that I can get a 1 there reasonably is I'm going to have to do some fraction business. So I'm going to have 1/7 times row 3 to give me a new row 3. 0, 0, 1, negative 2/7, 1/7, 2/7. The first row, at least, is nice as far as starting out with the 1, 0, 0. So that's actually set to 0, negative 1. That should be the rest of that one. And that leaves us with the second row. We like the 0, we like the 1, but the next thing that we would want to have showing up is a 0 in that third column. So to get that 0 in that third column, we're going to have to take a positive 2 times our new row 3. We're going to have to add that to row 2 to come up with our new row 3. Excuse me, new row 2. Brain. Well, brain's firing this morning. Gotta take that. 2 times that, plus that, give me the 0 that I need. 2 times this, so that's a negative 4/7, plus a 1, well, that's going to give me a fraction of 3/7. Two times 1/7 plus 0. And then 2 times 2/7 plus the negative 1, so 4/7 plus the negative 1, giving me a negative 3/7. Provided that I did not make any mistakes along the way here, the back half of our double wide matrix should be our inverse. So let's go ahead and copy that down. But then let's also finally pull out the calculator to check out whether this is correct. So we're going to switch over to the calculator. We're going to enter matrix C, and then we're going to see how we can find the matrix list of operations and pull out the inverse from there, or somehow otherwise find the inverse for matrix C, so we can verify if this is in fact correct. Fingers crossed that didn't screw anything up in there. for heaven's sakes. It could be one of those mornings. So, coming over to our matrix menu. And let's go ahead and scroll on down or select. Well, we want to go over to Edit first and select Matrix C, just for convenience sake. So we'll go ahead and take a look at that. That's listing for right now at 3 by 2. So 3 by 3 is what we would want. So if we hit Enter, that'll give us that extra set of entries. Now let's go ahead back to our document, and the first row is a 1, -2, sorry, a 1, -1, +2. So 1, -1, +2. Our second row, 0, 2, 3. 0, 2, 3. Our final row, 1, -2, 4. 1, -2, 4. And there we go. So we can go ahead and exit out of that matrix. Now we're going to want to go back to that matrix menu and select the name, Matrix C. We can go back to our menu of matrix stuff and look in that middle category for any sort of matrix math that might fit the bill. So if we start looking through there, we're not seeing any sort of inverse business that's listing. We keep on scrolling down, see if there's any sort of inverse mention. Look at that, they let you actually do those row operations one at a time. But eventually we scroll through all those possibilities and they don't have anything listed there. So, oh no, what are we to do? Well, if we exit out of that menu, and let's come back and take a look at this now. This is notation that we've seen before in different circumstances. We've seen that literally as a power. We've seen that in reference to inverse functions. We're now seeing it in relation to inverse matrices. So maybe that's popular enough that it already appeared. Wait a minute, that's the button we've been hitting all along to bring up that matrix menu. So let's give that a whirl and see if that will do the trick. If we hit Enter and we get a matrix that we can then compare to the one that we created together, well, look at that. It's giving us a matrix. This should be the inverse matrix, but clearly the things that are showing up there at first are not very friendly. So if we go to our math menu, we can convert those entries to fractions. And so 2, 0, -1. 2, 0, -1 down there at the bottom of the screen for our inverse matrix. 3/7, 2/7, -3/7. 3/7, 2/7, -3/7 for our second row. Oh, please let that bottom row be correct. -2/7, 1/7, 2/7. Oh, thank heavens. That is our inverse matrix. We figured it out by hand, but clearly using the calculator was far more efficient. And so, as often as we can possibly get away with it, well, let's go ahead and use the calculator. Let's use that tool to our advantage. But if we did, push come to shove, need to actually work through things by hand to find the inverse matrix, then we could go ahead and do that. And the reason why we're actually interested in this is so that we can come back to that discussion about solving systems. And so a different way of looking at a system is to say, if I take that system and only write down the coefficients, and I write down a matrix based only on my variables, and I write down a matrix only based on my constants from the right-hand side of my equations. The variable matrix and the constant matrix would have to end up being columns for things to work out properly. And what we could do is effectively set up a matrix equation coefficient matrix times variable matrix equals constant matrix. It's kind of like, let's catch all of our equations in one shot, in one equation. That have matrices, yes, but one equation, boom, if I solve this, I can get the solution to my system. That's a pretty sweet deal. In order to accomplish solving that particular matrix equation, we're going to need the inverse matrix. That way we can multiply by the inverse matrix out front, create the identity out in front of our variable matrix. Well, the identity matrix isn't going to change things, so that would give us our variable matrix by itself. We're multiplying out front, and that's very important. So we've got that inverse matrix times, out in front, times the constant matrix. So if we do this, then we're going to be able to bang out our solution to the system as long as the inverse matrix actually exists. So in this particular case, let's go back to the calculator, let's enter matrix A, and using the calculator, let's find that inverse matrix. So, back to the calculator, back to our matrix menu, back to our edit feature, selecting matrix A, and informing the calculator that we would now like this to be changed to a 2 by 2 matrix. And then we can enter the first row, 2, -3, 2, -3. Oops, that didn't work like I was intending. 2, there we go, -3. The second row, 3, 5, 3, 5. Now we're going to go ahead and backtrack out of the matrix. Re-enter the matrix menu, select matrix A, and then tell it to calculate the inverse. Not nice, so that we're going to go ahead and do that same thing again of going to our math menu, converting to a fraction, and seeing what comes up. This is a little bit nicer to write down then. For our inverse matrix, we're going to have the first row as 5/19, 3/19. For our second row, -3/19, 2/19. So this is our inverse matrix. We're going to want to take that inverse matrix and multiply it by matrix B. So let's go ahead and we will come back to our matrix menu. We will enter matrix B, that we would want to have a 2 by 1 matrix. That matrix B would have a -7 and a +8. So -7, +8. We're going to get out of there. We're going to take our previous answer, which is that inverse matrix from A. We're going to multiply it by, bring up our matrix menu and select matrix B. And we seem to be getting an answer here. We would like to now convert that to fractions so that we can try to get a nicer type of answer here. So it looks like our answer is shaping up as a -11/19, 37/19. -11/19, 37/19. And that would mean that that should be exactly our variable matrix. In fact, it might be better for us to actually go back and fill in a little bit more detail there with that matrix multiplication. So let me go ahead and backtrack there for just a minute after we finish writing down the solution. Again, this is something that we could go through and use our calculator to check. We've got several different ways that we can check this now. We can literally use our calculator to check this by going back to that original system and saying, with the help of my calculator, let me plug in x equals negative 11 over 19, y equals 37 over 19, check it out in the first equation, check it out in the second equation. I could go back to the original system, I could type in the matrix version of the augmented matrix, where my coefficient matrix is immediately followed by that last column, negative 7 and positive 8, and I could tell the calculator, convert this into reduced row echelon form and see if I end up getting my last column to be this same thing again here with the negative 11 over 19 and the 37 over 19. So those are just a couple of ways that I could go back and check that. But I'm going to flesh out that previous step there where we listed out the matrix multiplication by putting in matrix A quite literally and writing in matrix B quite literally, so that you have a reference there for what we've done that is more specific to the actual matrix letters that we've used and the matrix entries that we would have to use, and we get that same sort of column matrix that we originally wrote down showing up here. So a little bit more meat on the bone by throwing in that extra commentary here for how things can work out. So now we've got a way of using our inverse matrix in order to solve a matrix equation where we take our inverse matrix times our constant matrix. So now this offers us another opportunity for finding our solutions to systems. But I mentioned very quickly, and it might have gone just right past you, we've actually got to have an inverse matrix. If we don't have an inverse matrix, then this particular process isn't going to work. So there is that distinct possibility that if you were trying this because this is your preferred way of working through systems, you get an error message when you try to find that inverse matrix. Well, if you get an error message, then you would have to backtrack to one of the other ways that we've discussed for solving systems, whether that's using the augmented matrix converted to reduced row echelon form, or actually working with the system itself and not using matrices at all. So you'll have clearly plenty of options, and in fact what we're going to talk about is another particular way of working through systems that's going to use a different matrix tool. So that's coming up.